Hello, everyone. My name is Dennis. I am a PhD student at Martin's lab at EPFL. And today I would like to tell you a story about how a piece of software came to be. And as many stories about software, it starts with someone being pissed off at something really bad. And this one is not going to be an exception. And before we start, I would really want to tell you a bit my background in programming and how it all started for me as a programming experience. My very first programming language was Pascal. So how many of you here know Pascal? Can you? OK, that's good. Excellent. So to be honest, actually, I have some kind of irrational feelings toward Pascal, even though it's a weird, extremely verbose language. Even though it's the version of Pascal I used was still without GC, was low level, was really kind of C-style language. It was actually quite hard to shoot yourself because everything was so verbose. So you would actually have to be very explicit about shooting yourself. So you would be like, I'm shooting myself in the foot right now. And even though it was a low-level language, it was really hard to shoot yourself, though. After Pascal, I learned C. And my first experience, when I just started coding stuff in C, was I'm so much more productive now. I can write so much more code because everything is so tense and so compact. There's a nice notation for everything until you realize that all this nice notation can explode in weird, arbitrary ways. And it's surprisingly easy to, yeah, that's my back. OK, it's surprisingly, it's fine. It's surprisingly easy to accidentally just do something wrong because it's language is optimized for some weird assembly-like coding, and most apps are not like that. After C, I learned CSharp, and it was my first object-oriented language. And it was actually kind of one of the biggest wow moments I've had in my programming experience, because classes were really not a trivial concept and took a while to grasp. But still, in C#, actually, even though not many people use those features, you still have all of the nice low-level stuff like structs and pointers and that you can use to optimize stuff if you want to. And in C#, I never felt like the language is too high level because there's always, you can make an obvious choice to use pointers in C#, and it works perfectly and it's fast. And C# was also my first language with IDEs, and it was kind of the only IDE experience that I ever liked because everything was so integrated. I guess everything else doesn't quite live up to this experience anymore. After that, I learned Python, and my main reason for switching from C# was because it wasn't going anywhere. It was a Microsoft-only thing that lived in Microsoft-only ecosystem at the time, and there was no way to run apps outside of Windows. And Mono was just starting at the time, and it was really kind of hard to justify using C# for non-Windows apps. So I learned Python. It looked really cool, and it was, again, even more productive. But at the same time, it was only productive until a certain specific threshold, somewhere around from 1K to 5K lines of code. Suddenly, you start losing touch with your code because lack of types actually starts hurting you. Probably until a few K lines of code, Python is actually, in my experience, more productive than type languages because you can still hold everything in your head until that limit. But when you get to big apps like 10K and more, or even something horrible, I've heard horrible numbers about Dropbox code base in Python, and so when it gets this big, you cannot hold stuff in your head anymore, so you really need a tool to help you out. And it was really obvious in Python. Python doesn't quite work for this kind of use case. And at the time, I was just writing apps in Python and Qt with PyQt and just doing some consulting and so on and so forth. And I stumbled upon a video from some conference by Daniel Spielk that explained how hierarchy types work. And for me, at the time, it was completely incomprehensible because I was just a normal Python developer. I didn't even know that such a thing existed before because in C#, generics are simple. There's no hierarchy types, and I was completely blown with all those kinds and so on and so forth. And it looked so hard, and it actually made sense to learn it because I was like, it looks so awesome. It's probably cool, right? So there's no way something this great looking can be bad. And this is how I kind of happened to learn Scala. And actually, I came to Scala because of the weird, obscure features that I didn't even know how you should use. But I stayed here for all of the nice stuff that you also have, like types which don't get in the way. With nice type inference that actually infers most of the things you actually are horribly complicated in languages like CSharp of the day. And everything is fast until before everything is warmed up, you kind of feel, is it really a fast language? Because JVM is really weird beast, but after it's warmed up, it's fast, of course. And you have all the nice parallel libraries and so on and so forth. So I really kind of like came for higher kind of types, stayed for everything else in Scala. But still, I like the language, but there was something that kind of felt like out of place for me after having had experience with all of the previous languages, as I said before. And this part was kind of the environment where Scala runs. And I kind of prefer to refer to this environment as a golden cage because it's really, really nice, actually. But it's a cage. So there are a few kind of annoyances that I'm not quite super fond of. So first of all, Warmup Time is my absolutely least favorite feature of JVM. And it really takes a while to warm up. It really takes a lot of effort to make a proper benchmark on JVM because of the weird, hardly predictable stuff that JITs do. And I really kind of like happen to really dislike JITs after JVM, even though I have some very good JITs which are not as slow to start. Also, a kind of like interaction between JITs and compilation in your code and how it's all kind of like doesn't happen to be predictable at all. It's something that I truly dislike. And another thing is, as on JVM, you're kind of like forced to live in the sandbox where everything is super safe, super high level, and if you want to do anything arbitrarily, just a little bit more low level, like you want to use raw memory access, suddenly it becomes extremely hard because JVM has this like ultimate vision of being the safest platform with all of the security management, with all of the safe features and so on and so forth. So their goal is not to expose you any kind of detail about how platform work. And sometimes you really need that because for some apps, like GC is not enough. Like for some apps, you would really want to kind of do something more level. And on JVM, it's extremely hard. Of course, you can use something like sunmisc unsafe, but this is like even worse than C, so I don't know. Another thing that's really, really hard on JVM is it's really hard to interoperate with anything but code on the JVM. So if you want to kind of call to like Python code or C code or C++ code or any other code which is not in JVM ecosystem, which is not compiled with some JSON or something like this, it's suddenly impossibly hard. And the reason why it's impossibly hard is because JNI, and JNI is like the most complicated interop layer I've ever seen in my life. And that's the only layer you can use on JVM, of course. So now you know stuff I dislike, so let's kind of daydream for a second. I really like daydreaming. Sometimes I daydream so much that I lose a distinction between which features are real and which are not. Yeah, but that's not a problem. So first of all, I would like Scala to be immediate. I would like to start my apps and have them run just as I said. You know, in 2016, we have extremely fast machines with extremely fast SSDs, and it still takes seconds to start SBT. You know, this should not happen in 2016 anymore. Also, I would really like to have something apart from reference classes. I would like to have some way to have some reasonably powerful value types in a system. So I would really want to have structs. I would really want to have low-level like backs of things. Like, right now, if you want to have any kind of like non-value thing, like a single value, like more than one value, like for example, let's say you have a point in 3D space, like it's represented by 3 numbers. You have to allocate, and that's kind of not good. You really need to be able to have values and allocate them on stack and pass them by value and so on and so forth, because it's actually a thing that actually works very well, and compilers can optimize it to produce impressively fast code. And lastly, I really want to have a bit more control over memory management, because for some apps, you really need to go lower levels than your normal GC stuff. And so far as experience with GC has taught us on JVM that there is no perfect GC. Whatever you do is always a trade-off. You always either sacrifice latency or throughput or predictability or something else. You can never have everything, like you can never have it all with GC. And the thing that you get always with GC is like nice ease of use and kind of no burden on a programmer, even though you actually do have a burden when you get performance issues. But actually, in some apps, it's actually surprisingly easy to do a bit of lower-level memory management, and you have no issues that are common in GC systems. And lastly, I really want to call other languages. I really want to call C libraries which are fast. I really want it to be easy and not to take me more than like a few hours to write the bindings for some library. I don't want to kind of like just deal with GNI ever again. But you know, daydreaming is nice, but sometimes you just need to wake up and realize that like whatever you dreamed is not real, right? And you just go back to your day job and just you go there and just get a new task from a boss that says, you know, we have this old legacy code base in C++, and now we have everything in Scala, so it obviously has to be ported to Scala because it's better. So you get this like ugly, large mess of a code base, which does some really weird domain-specific knowledge thing. So you try to understand what it does, you split it apart, you try to understand what our pieces do, and you see that here, oh, here we have a vector, which is actually just a struct that bundles three values together, and it has this nice mess-looking like operations on them, so it's actually quite simple. Then you have this racing, you have this enum. And it's actually like, slowly you read through the code and you realize it's actually, even though it's C++, it's actually possible to understand what it does. Yeah. So you start just maybe like refactor it a bit, like maybe add some commons tests and before you port it, so you see that there is some weird like bits and pieces. And then you suddenly stumble on this like thing, which is a large piece of domain-specific knowledge that you cannot touch, of course. Yeah. So on and so forth, and you slowly kind of it takes you a few weeks to understand what it does, and then in a few weeks you come back to a boss and say, oh yeah, I ported it. So now it's in Scala, so it must be fast, right? So we port everything to Scala. The vector we've had before becomes a class vector because we don't have structs, right? And everything else becomes a class, and everything else becomes like high level and nice, and and this domain-specific thing we've seen before is almost fine because we actually split it into like more or less manageable code. And it all looks good until you realize that this code you've had before actually is not the same as what you have now. So you compile the previous one, you try to see how much it takes, and you see it's a small thing, it takes a few seconds, and it's not too bad, so it's like 7 seconds to run, it's nice, yeah. So then you come back to your port in Scala JVM, and on JVM, and you just try to compile it first. It takes a while, of course, because it's SBT. And then you launch it, and you see there is a noticeable slowdown somehow. You're not quite sure, so it takes a while to understand why is it slower. You try to benchmark it, you use profilers, you try to understand what actually happened, and why is it almost 2 times slower. And then after a while, you just realize that this vector things are causing extreme GC pressure, and your app that used to use 10 megabytes of memory now happily is able to consume gigabytes of memory somehow. And you just really want to cry a bit because there is no other way to do it, so you start considering other options, like doing maybe some kind of off-heap memory, using like byte buffers to store these vector things. And basically, at that point, your code base becomes C code only like backwards, because in C you actually have nice syntax for the things. In Java, when you deal with this low-level stuff, you end up doing some kind of weird arithmetics on offset in a byte buffer or something that doesn't quite help with your code maintainability. So you get really depressed after this. and you go somewhere like in Switzerland, in some village, and try to figure out how to make stuff better, and no one sees you for 9 months, and so you come back in 9 months, okay? And in 9 months, you have like something that you always wanted. So first of all, have this Anstract thing. So it's almost the same code as before, but it's a struct now. And you can actually not allocate it on a heap now, because it's actually just the value of 3 other values. It's actually quite simple. And basically have a very similar code, roughly unchanged, and you can actually compile it, yeah. Wait for it, yeah. OK. And then you launch it, and you see this like kind of nice swiftness of code that you've had before without random GC stuff that happens behind the scenes, because now you actually don't really do any GC here, because your app doesn't need GC for this. Like, you have some domain-specific mass-centric app here, so it doesn't need to GC even. So you're kind of like, it's a bit slower than C++, but it's like 20 to 30% slower, not 2x slower. So it's kind of more than good enough, and you're happy now, because you can finally get your stuff that you always wanted. And then you open source the thing, and then suddenly, randomly, lots of people come and try to use it, even before it's released. And people do lots of cool stuff, even though it just started. So first of all, like this thing was just a small team effort by me and Sebastian, even though Sebastian did not submit any commits yet to the repo. He, like, Scala Native is largely inspired by Scala.js architecture and Scala.js design principles, and Scala Native would not be possible without Scala.js. And I kind of like think of Sebastian as a second guy on a team. But then all these kind of people appeared and just started doing like cool stuff with this unreleased work-in-progress software. And I just started open a pull request to change many different things. And we've merged like, how many? 36 pull requests from 10 people, from 12 people in past months. And these pull requests really do different, like, they start from small typos and changes here and there to really cool stuff like FreeBSD support. Who here uses FreeBSD? Can you please raise your hand? 1? OK, 2? OK, 3. OK. So we need to support FreeBSD, I see. And they also tried to use it, and they even managed to somehow make it compile on iOS, even though I've never tried personally. But apparently, Timothy Klein was able to do it, so it's cool. They also write documentation for you, which is also quite surprising. And they write this nice guides on how to use it, even if there is no official docs yet. But this box Scala Native is probably the best place to clone, the best thing to clone if you want to try out Scala Native right now, before we actually release anything publicly. They also implement non-trivial stuff, they port non-trivial stuff, and it's really kind of cool that people just contribute things, and the velocity of project improved dramatically since Scala Days in New York. But that's kind of like the story of Scala Native until today. But what is actually like Scala Native? How does it work under the hood? And the short answer is it's an LLVM compiler. So it's an LLVM-based compiler that makes your Scala code produce native binaries. And when I say native binaries, I just say one nice binary that you can just take and like ship to a different machine, and it will just work. There is no VM. There is no kind of like setup. You only need all of the libraries that your project depends on. So if you depend on some native libraries, of course, you'll need to have that. But it's basically a simple thing. There is no a VM anymore, even though LLVM has a VM in it. We can also optimize tail calls with LLVM, which is, I think, is a very important feature for functional code that we used not to have properly on JVM. We used to have a subset of tail calls. We would not have mutual tail calls before. Another question, which is like a very common, is it the same language? You probably like changed everything, so because we have this like new stuff like structs and pointers now, it probably is a completely different thing, but not really. Scala itself is the same Scala that you already know. And actually, libraries that you use are also the same libraries. There's nothing ultimately surprising about what we do. It's just another way to compile your code. Another thing is just like it's probably like just a backend, right? You know, backend. Like how hard can it be to make a backend? Just make it like a piece in a compiler, and it's kind of emits whatever you want to emit, and that's it, right? But it turns out to make a nice kind of like experience for any non-JVM compilation target, you really need to be a bit more than a backend. You need to be a bit more of a platform. You need to have some internal representation, some internal kind of language that you use to maintain all of this magic behind the scenes, because actually having just a backend only works for JVM because Scala was designed with JVM in mind. But if you want to compile Scala into anything trivial, you really need to do something like this. So you need to have intermediate representation. You need to, like all of your front ends that you support, like for example, Scala C and .t, should emit this representation, and it should be reasonably high level. And then you have a piece that kind of combines everything together and produces your target thing. This is architecture originally originally first happened in Scala.js, and we just took it over as a nice working thing, and it was a nice working thing. And as you can see here also, we will support both Scala C and .t, and it's actually quite important to, because in .t we have lots of new cool things going on. Like for example, here this LTO box is this cool new thing that Dimitri is working on, and it's a link time optimizer that does all of the cool stuff with your code to remove all of the high-level features and replace it with lower-level features, so that when Scala native happens, it can compile low-level features into more low-level features that optimize the way to a constant, okay? As some of you might have seen on Doug Dim's presentation. But generally, it's .linker is a very cool thing that is going to happen in .t, and we would really want to support .t as much as possible and have it as a first-class citizen. So another question is like, does it GC? So you said that you don't have GC issues, but you probably still have a GC. And the answer is, yeah, we still have a GC. Currently, we use something called BoyMGC. It's quite a bit slower, like 2 to 3 times slower GC itself than JVM GCs. But it can only get better from there, right? So we already have some plans to improve this thing, so stay tuned. We'll probably do something else in this area, in this space in the near future. And of course, on Scala native, you don't always need to GC, because if you can express your TED loops in a lower level concepts, you can easily make it not GC at all. And then GC performance doesn't matter because you don't do GC. Hardware-wise, we've had interest in ARM and Intel, both 32 and 64-bit, on Unix-like operating systems. And currently, we're mostly developing on Intel 64-bit, but we plan to expand this in the future. Library-wise, like I said before, Scala native doesn't try to be the completely different like beast that you would need to learn. Actually, Scala native tries to be the most least surprising thing you can possibly get. And for this, we actually take an effort to port Java libraries and just make them work as if they were like on JVM. So we really take effort to make it least surprising environment for existing Scala developers. And it also should make quite easy to port existing libraries to Scala native, because you'll be able to just use basically the same code without any changes. And lastly, the question of when is a very popular one. When is it going to be released? When can we try it? So a first stable thing, like more or less stable thing, like a first preview is going to be released in the near future. You can already try it. Like the thing I've shown you before, POSC Scala native is a nice repo that you can clone, and you can actually follow the instructions and have it built basically already. It will be a bit nicer in the future in 0.1 because we will add some actual documentation and so on and so forth. And from then on, we plan to stick to monthly updates to kind of to make sure like that we can quickly evolve the project to a stable thing. So if you want to get updated when this happens, we'll most definitely post this on Twitter and in our Scala native Twitter account. So if you follow that, you will most definitely see a tweet about how we became stable, for some definition of stable, of course. So that's about it. Thanks. So questions. So I think we have people with mics walking around. Can you? Oh, yeah. Okay. Cool. Yes.
Hi. Will there be some compiler for Java source code or bytecode so you can port other libraries as well?
So right now we don't plan on having anything like this in near future. So at the moment, our current strategy is to port stuff to Scala. It's actually quite easy. So most of the time when we port stuff, it takes barely like a few hours per 1,000 line of code or something, because code usually gets smaller when you do this, so it's nice. We don't plan to have Java bytecode or Java source support in any kind of near future.
OK, thanks.
So thanks. Going forward, do you think that you want to go in the same direction as Mozilla's Rust language? They have this borrow checker, which is essentially, it kind of feels to me like all the Scala type safety, but applied to memory primitives.
Yep.
So do you want to do something similar, or really just provide a way for me to allocate a struct on the stack or on the heap?
So it's a very good question. So the question was, do we want to be more like Rust in the future? And the answer is, we cannot be more like Rust unless we completely change language in non-obvious ways. So Rust has a very interesting, extremely powerful type system to control ownership in the type system. So in the types, you know, for each and every allocation, is it owned by some other allocation? And this allows this kind of nice, to construct this nice trees of allocation that are automatically deallocated when your tree root disappears. The problem is that in Scala, very often you don't have tree-like graphs of allocations. You very often have loops. And it's extremely easy to get loops with closures. It's extremely easy to get loops with inner classes. And generally, it will be from borderline impossible to make it work with Scala, in my opinion, because Rust only works because it was designed with this kind of concept in mind. I would really want to explore a bit more in a space of memory management, in semi-manual, semi-automatic memory management. And I think a concept of regions will probably work better for Scala native, because regions can actually impress cycles, and they're also quite fast. So we'll probably explore something in a more lower-level memory management techniques, but it will most likely not be something like Rust, because that doesn't work for Scala, unfortunately.
Yes, so one of your motivations behind this was to either reduce GC or remove it in the resulting binary. So as a user, is there a way for me to find out how much GC my Scala native application is using?
So the question was do you have any kind of infrastructure to profile right now on Scala native? We already work with native profilers, like for example, on Apple operating system, you can use Instruments. Instruments is this nice graphical profiler that lets you kind of shows you where your hotspots and so on and so forth in your native apps. It just works with Scala native. And in our case, GC is just a library, and it's actually possible to see if something GC is too much, because you will have too much time spent in functions named GC underscore different names. And it's actually should be quite easy to see how bad GC impacts your app just looking at the profiles. Yeah.
Me?
Yeah.
I have a mic, yeah, so I guess that's me. So I see you implemented several namespaces from Java. So when do you expect a lawsuit from Oracle?
I'm sorry, what?
Sorry, maybe not a very successful joke, but I mean, apparently you implemented certain classes from Java namespace.
Yeah.
Right. So And we all know that there was a story about the Google and Oracle lawsuit recently, and
yeah,
it seems quite similar case to me, isn't it?
So all I can say is that in the final case, Google versus Oracle, Google's use of Java APIs was fair use.
But still copyrighted.
Yeah, so it's fair use, I guess. But generally, like, no comments. I'm not a legal person, so you should probably ask these questions to a legal person. Yeah.
What about Spark and Scala Native?
Spark is a very interesting app we want to run eventually. Right now, we're blocked basically by how much we implement of JDK to make libraries like Spark or Akka happen. But I'm definitely interested in seeing like large frameworks that we already have to run on Scala Native. So it basically is bound by us having a reasonably complete implementation of those. Once we have those, it should be doable to port stuff. We already have Akka on JavaScript, so it should not be, for example, impossible to have equivalent thing on native. And for Spark, it's a bit bigger code base. I cannot definitely say how easy it is, but I would say we probably see Akka on native before we see Spark on native, and from there on, it can only get better. Any more questions?
Yeah, one here.
Yeah.
You mentioned you don't like the JNI. I think nobody likes it. But what are your ideas on how to get interop with other languages?
Okay, cool.
On Scala?
That's a very good question. I'll just show you a small snippet that we actually have. Basically, interop with C. So right now, we are starting with C as a first language. We interop nicely with. So this is how it looks to call a C function from Scala Native. So you define a thing called extern object. Extern object is basically just a place where you put all of the signatures for C stuff you want to call, and that's it. That's all you need. You don't need to write any proper C code. You don't need to do any kind of weird magic, that, like any weird environments that GNI makes you do. That's all you need to do. Basically, that's all of the code that is required to call malloc. And it will automatically, you can also specify what libraries you would like to link with when you use this function. So for example, when you use malloc, for example, I can imagine people using gmalloc, which is a better malloc. And you can annotate your external objects with link. It will automatically also link with native libraries that are necessary. So it's super easy. And in the future, we're interested in supporting more languages. I cannot promise you anything there, but we have an issue in the backlog called Objective-C interop. Yeah.
So my question is also about interoperability, but in the other way. Do you plan to make it easy to use Scala native developed modules from inside the JVM Scala?
So Scala native, like the question was like, how do you call Scala native from JVM and the other way around? And the answer is Scala native lets you expose stuff over C ABI, and JVM lets you to consume stuff over C ABI. So it should be quite doable to just use GNI as a boundary if you are brave enough. But short of that, we don't plan to have anything more than that because, again, there is only one way into JVM from native code is GNI, and that's basically kind of the thing, yeah. Yeah. Okay, so the question was, how do you distribute code in Scala Native? The answer to that is this NIR thing over here is basically, you can think of it as our own bytecode, like Scala Native bytecode, which is the things that you will distribute in jars. So it's very similar to Scala.js. In Scala.js, you publish SGS-IR. In Scala Native, you'll publish NIR. So basically, you publish bytecode, and then you only compile native code like when you get all the bytecode for everything, and then you link it, and you get a native binary. Yes?
What about network and threading?
Network and what?
Threading.
Threading. So at the moment, in 0.1, we're going to be single-threaded like Scala.js. but it's an implementation restriction that we will most definitely fix before 1.0. So we'll plan to have parallelism. So basically, that's starting part and networking. So we'll have Java NIO stuff and Java IO stuff and Java Net stuff. So basically, all the APIs you already know. So you will not need to learn anything new. Yes?
So you've been speaking about...
Sorry. Yes? Basically, the question was like tasty. What happens when tasty happens? So when tasty happens, this picture can potentially simplify, and we'll not need to publish Java classes, Scala.js classes, and NIR classes, and everything, like in many different like cross projects. Hopefully, like right now, it's like not in the state yet, but hopefully when tasty is finally there and stable, we'll be able to just publish tasty, basically. That's kind of like the thing I would like to see in the future, but it's a long road to get there, and we'll have this NIR thing before it happens. But tasty definitely looks like a thing that can potentially make it easier to distribute stuff just once, but it's yet to be seen if it works out. Yes?
Yes. Can you hear me? Oh. So I wanted to ask you, you've been detailing what is the translation that with this Scala native you save a lot of allocation, or that you make it more quicker on the using of the stack memory over heap memory. That's part of the motivation, the shift.
Yes, of heap memory.
I wanted to ask, how is there any difficulty, or which will be the challenges that you could find in the translation regarding any other issue like basic arithmetic instructions from the JVM to the LLVM intermediate representation, or in particular concurrency primitives? Do you have any difficulty there?
So let me ask, so did I understand the question correctly? So you're asking why can't we just do it on JVM, like to experiment with memory management?
No, what I'm doing is which are the challenges you may have found regarding basic arithmetic instructions, the semantic of basic arithmetic instructions and types when translating from the JVM to the LLVM, the intermediate representation of the LLVM.
Okay, so you're asking what kind of instruction we are missing on JVM, basically, and that are available on LLVM, is it right?
If is there any problem or any mismatch between the meaning of the instructions between the JVM or the LLVM?
So basically, this NIR thing is our own, like essentially our own instruction set that we map to LLVM. It has more features than JVM bytecode, and not all of them are expressible in JVM bytecode. Like for example, structs and pointers at the moment are not easily expressible in JVM bytecode. And in LLVM, because it's essentially a high-level assembly, it's like lower-level C or something, I don't know. High-level assembly that is also happens to be mostly platform-dependent. You can actually express anything you want in LLVM. There is no kind of restriction what you can do in LLVM. It's basically like you're only constrained by your own kind of like creative vision or something, I don't know.
One more question about it. Is it easier in the LLVM to represent lambdas in particular, or anonymous function, or any in general function objects?
So none of these things exist in LLVM. LLVM is super low level. It has top-level functions, it has pointers, it has structs, and that's about it. That's what we compile to.
Okay, I am asking because I think that there was a problem for the Java for the people who develop the Java compiler, that getting lambda anonymous function at least into the language, and I don't know if it was related to the JVM. Thank you.
I think I don't quite understand what you mean, so let's take it offline. Yes? So I can show you how it looks like. It is human readable for some definition of human readable. Yeah, we have a docs branch, which is a bit outdated. This is why it's not merged yet. So in this docs branch, you have NIRMD. And how it looks like is basically like a bit like this. So given this source file over here, so you have an object that says hello world, okay? This is how it looks in NIR. So first of all, it's an SSA basic block thing, similar to LLVM, But the main difference is that it has high-level features like classes, modules, as instance ofs, is instance ofs, and all of the things that we need to do Scala. It also has closures and so on and so forth. So it's actually quite a bit of stuff over LLVM. And our main challenge in the toolchain is to remove all of the high-level features and replace them with lower features. And as I said, features in LLVM are very low level. Yeah. So you can actually look through. It's a bit out of date, but just slightly. So it's topic docs, basically, web docs. Okay. So right now, we've had, in our Gitter community thing, people running it on FreeBSD, Linux, and Mac at least. That's the one that I know of. Maybe someone managed to, and also I've seen iOS demo. So generally, we are not very bound by the hardware architecture because LLVM is quite, we use LLVM in ways which is not very platform dependent. So basically, it's very easy to port it to more architectures if someone wants to. Basically, the only thing we don't support right now is Windows, okay?
Are you going to provide any debugging tools? I mean, on the native layer,
So the question is, how do you debug this thing? And the answer is, right now, is use LDB. It will not be super high level. It will show you stack traces. It will let you look at the assembly, and soon you'll also be able to correlate assembly to a source code in Scala. So it will get a bit better over time and get a bit more high level over time. And I think Apple tools are built on LLVM infrastructure, so you might also be able to use Apple tools eventually to debug this thing. Any more questions? Okay, I guess not. Okay, cool, thanks.